Hey folks, welcome to your first lesson on electricity. In particular, we're going to be talking about electrostatics in this one. So we've got 3 learning goals for this lesson. First, we want to be able to explain on the atomic level how objects actually become charged, how that static electricity actually happens. Second, we'll talk a little bit about the difference between conductors and insulators. And lastly, we will talk about 2 different ways that we can see these electrostatic phenomena happen. One is through conduction and the other is through induction. Okay. Now just some basics. This is probably a review for you. If so, awesome. If not, listen up. Basics on electric charge. First of all, we've got 2 types of charge that an object could have. It could be positively charged or it could be negatively charged. What we find in nature is that opposite charges will tend to attract each other, so a positive and a negative will be drawn towards each other, whereas charges that are the same type, so either 2 positives or 2 negatives, will tend to repel each other. They'll push each other apart. Now the reason that we get charge in the first place is because of the structure of our atom. Here's a little picture of an atom similar to the one that I drew in our last class session. Now in the middle of this atom we've got a nucleus that contains protons and neutrons. Protons have positive charge, giving this nucleus an overall positive charge, whereas these electrons orbiting around the outside of the nucleus have a negative charge. Now then, the way that we can give an object a charge then is to have its atoms end up with unequal numbers of protons and electrons. Usually we would expect that the number of protons in here equals the number of electrons out here. If we were to mess up that balance, that's how we give an object a particular charge. Now the way that we do that specifically is by changing the number of electrons, because if you notice our protons are pretty well sheltered here in the nucleus at the center of the atom. It would be pretty hard to dive way down deep into the middle of the atom and either take away protons or add protons. So then the way that we can change the balance of protons and electrons in an atom is to either add more electrons to the outside or take some of these electrons away from the atom. Now, the effect that this has on the charge of the atom is a little counterintuitive because if you recall, our electrons are negative. So that means if we add electrons, we've got more negative charge. So adding electrons gives a negative charge to the atom, whereas if we take away electrons, then we've got more protons than electron and an overall net positive charge. I know that seems a little counterintuitive that adding electrons gives a negative charge and removing them gives it a positive charge, but that's just the way it is, folks. Sorry. Okay. Now later on we're going to want to be able to quantify charge. Just so you know, the way that we do that is using the unit coulombs. C-O-U-L-O-M-B. Coulomb. That's our unit of charge, the same way that gram is a measure of mass or meter is a measure of length. Electrons and protons each have the same charge, the same number of coulombs, except since electrons are negative, their charge is negative, protons are positive, so theirs is positive. If you note, this is a very tiny, tiny number. We're talking about 160 with 18 zeros in front of it with the decimal point way out front. So we're talking a very small amount of charge on each electron or proton. And so we need a lot of atoms to add up to any sort of significant amount of charge. Okay. Now one thing to know about charge is that it is always conserved. We cannot create or destroy charge. The amount that we have is the amount we have always had, and it's the amount we always will have. So the way that we end up with an excess charge on an object is to transfer electrons back and forth between 2 things. We can't just cause our electrons to disappear or appear out of nowhere. We've got to move them somewhere. Right? So that means that when we, in our stations the other day, charged our balloons by rubbing them together, it's not like the act of rubbing the balloons together caused electrons to appear out of nowhere. What happened was there was a transfer of electrons that occurred in the process of rubbing the balloons against various objects. So just so you can see that a little bit better, we've got a nice little simulation here. So we've got a balloon which has a neutral charge right now, equal numbers of protons and electrons. And then we have either your hair or your sweater or whatever it is. Again, we see the positive charges representing the protons, the negative charges representing the electrons. And if we look, our sweater overall has approximately an equal number, so it's also neutral. It has no excess charge on it. Now, when I take this balloon and start rubbing it against that object, basically the friction from that rubbing will cause some of those electrons from the sweater to get moved over onto the balloon, just because of the fact that we're rubbing these two things together and some electrons end up getting shuffled in the process. Okay? So once we've done that, now my sweater has an overall positive charge because I've taken some electrons away. And my balloon now has extra electrons, so it now has a negative charge and can start to interact on an electrical level with other objects. So if I let this balloon go, we see that these opposite charges attract each other, which is why we can then get our balloon to stick to our hair or to our shirt or what have you. So let's talk about how this then relates to the stations that we tried out. Okay. So one of the stations that was out there was for you to take two balloons, rub them against your hair, and then try to bring them together. Now what you should have found, and if you didn't, feel free to try this again at home and see if you get better results. What you should have found is that those two balloons then repelled each other. The reason for that is, just as we saw in that simulation just now, both balloons ended up taking some of the electrons away from your hair. That caused both of them to have an excess number of electrons so that they were negatively charged. And so all those excess electrons in this balloon repelled all those excess electrons in that balloon, so they pushed apart from each other. Okay. Now on the other hand, when you rub the two balloons together, when that happened, the only way for them to transfer electrons was to and from each other. They couldn't get extra electrons from your hair or any outside source. So when I rubbed two balloons together, what ended up happening is one ended up stealing electrons from the other one. So this balloon stole electrons from that balloon. That meant that this balloon lost some electrons and now has more protons, so it's positively charged. This balloon has extra electrons, so it is negatively charged. Then when I bring the two of them together, since they have opposite overall charges, they attract each other. Now I know that this probably was the hardest station to coordinate and get to work, so if you didn't see that happen, that's okay. Feel free to get a couple balloons and try it out at home if you would like. All right. Now, what you hopefully have noticed is that it's not like every time you rub two things together, suddenly they are electrically attracted or repelled by each other. That's because not all objects gain charges easily. For some it's easier, for some it's harder. Okay? So we've got three major categories of objects, ways to describe them that indicate whether they take charges easily or whether they don't tend to take charge. Okay? So our first category of objects is conductors. A great example of conductors is metal. Okay? Conductors are the type of material that transfer electrons very easily, so it's very easy to give them a charge. And what's more is that once a conductor gains a charge, it's going to spread that excess charge out evenly across the entire object. Okay, so if I put a charge on the end of a piece of metal, those extra electrons that I've given to my metal will evenly disperse themselves across the entire object. Okay. Now on the opposite end of the spectrum, we've got insulators. Some good examples of that are wood, plastic, rubber, etc. Okay. Insulators tend to be pretty resistant to transferring electrons. They don't like to take extra ones. They don't like to lose the ones that they've got. They tend to like to keep things the same way. Okay. Consequently, if I can manage to get an overall charge on an insulator, take away a few electrons or give a few extra ones, that excess charge just stays in one place. It doesn't tend to spread out over the entire object the way it did in conductors, which is why you may have noticed with your balloons, they're actually insulators. They're pretty resistant to gaining a charge. So when you did give the balloon a charge by rubbing it against your hair, the only part of the balloon that really interacted then, attracted or repelled other things, was that one spot on the balloon that had contact with your hair. The rest of the balloon didn't really have any sort of overall charge. The third type of object is just in between conductors and insulators. We call them semiconductors, semi meaning half, so they're like halfway between insulators and conductors. Silicon is an example of a semiconductor. Just FYI. All right. So we've talked about how readily objects will tend to take a charge. Lastly, I want to talk about how do we actually give a charge to an object. Now there are two ways that we can do this. One is pretty straightforward and the other is a little bit trickier, so we'll spend a little more time on it. The first way that we can charge an object is through conduction. Now this is sort of the intuitively obvious way of conducting or giving a charge to an object. Basically, we put that object in direct physical contact with another object. Electrons actually get transferred from one object to the other. So every time that we were rubbing balloons against our hair or rubbing them against each other, that balloon was in direct contact with something that could give it more electrons. So those were all examples of charging by conduction. Okay. Now another way that we can kind of charge an object is through induction. Now the tricky thing about induction is that electrons don't actually end up getting transferred. It's not like I'm actually giving excess electrons to another object. But what happens is we can kind of manipulate the excess electrons on that object so that one side of the object is a little bit more positive, it loses its electrons, and the other side is more negative. All the electrons have migrated over to that side of the object. I know that maybe is a little unclear, so I'm going to show you a picture in just a moment. Okay. So first of all, charging by conduction. Okay. An example of that would be when you charged the balloon against your hair and then touched it to the knob of the electroscope, that funny little device that had a knob at the top and the two metal leaves at the bottom. Okay. So our electroscope starts out like this. We've got our protons and our electrons pretty evenly distributed over the entire electroscope. Now when we touch the balloon to the electroscope, some of the extra electrons that were in our balloon spread out over into the electroscope. What that does then is it gives an overall negative charge on the electroscope. That charge spreads out down into the leaves and through the entire top as well. And then both of our leaves have a negative charge, which is why they repel each other, because they're both negative, have extra electrons, so they push each other apart because those similar negative charges don't want to be close to each other. Okay, so this was an example of conduction. We actually physically moved more electrons into the electroscope. Now when you charged the balloon but you didn't actually touch it to the electroscope, you just brought it close by, this is an example of induction. So we've got it was actually a balloon in our case, in this case they call it a rod, whatever. We've got an object with extra electrons on it. Okay? Those extra electrons are giving this object a negative charge. Now what happens then is all the electrons that are up here at the top of the electroscope are repelled by these electrons, so they run away down into the leaves as far away from these electrons as they possibly can. Okay? That means that at the top of the electroscope we've still got all of our protons hanging out. So we've got an overall positive charge here because we've got our protons but our electrons have kind of hit the road. Down here on the other hand we've got all these electrons plus the electrons that were already down here. So we've got a negative charge down here. Since those leaves are again overall negatively charged, the leaves repel each other. Okay, so note that what happened here is we didn't actually add any new electrons to our electroscope. We just kind of scared the electrons that were already there to all run down to the bottom of it so that they could get away from the extra electrons here. So this is an example of charging by induction. No actual transfer of electrons, but a redistribution of the charges so that we still see some of those electrical interactions happening. Okay. Now, if you recall, our goals for this lesson were as follows. First, we wanted to figure out how objects gain charges. We wanted to distinguish between conductors and insulators, and we wanted to talk about the difference between conduction and induction. So as a way of sort of checking yourself to see if you really learned all three of those things, I've got 3 questions here for you that I want you to take a minute, think about, see if you can answer them. If you can, that's awesome. If you can't, that's a sign that maybe you need to think of some questions to ask me or go back and rewatch the video. Okay. So our 3 questions. First of all, think back to the 2 stations that involve Scotch tape. In one situation where we had the 2 pieces of tape on the table and then brought them together, they repelled. In the situation where we had both pieces of tape stuck together, they attracted. Can you tell me why? That's the first question. The second question, the power cord that you use to plug in your computer, your phone, your iPad, what have you, has basically functions so that we can get electrical charges moving between your electrical device and the wall outlet that it's plugged into. Now, if you were to dissect that power cord, you would see metal wires in the middle, and you would see that the outer part of the cord is encased in either plastic or rubber. You should be able to tell me why that is. Last of all, think about an object that's being charged by induction. Does it have more electrons, more protons, or an equal number of both electrons and protons? Take a moment to think about this. If you need to pause the video to give yourself a little more time, that's no problem. Now, here are the answers that I would expect you to give me. First of all, those 2 stations with the tape. When we had the 2 pieces of tape stuck to the table, they both stole electrons from the table, so they were both negatively charged. That caused them to repel each other. Okay? I'm sorry. This says because they both stole electrons from the table, making them both positive. It should be negative. My apologies. They're both negatively charged. Okay. Whereas when we had tape stuck to another piece of tape, one piece of tape stole electrons from the other one, which means that the one that stole the electrons was negative, the one that lost the electrons was positive, and then they're able to attract each other. Okay. For the second question, your power cord has metal wires in the middle. Because that metal is a good conductor, it's going to take that charge from the outlet and quickly send it on up to your computer and then back again. Okay. Now the plastic or rubber casing on the outside, that's serving as an insulator so that when you grab your power cord, the charge doesn't then come up into you and give you a nasty shock. Lastly, objects charged by induction. I know this is tricky, but they have equal numbers of protons and electrons. We haven't moved any charges. All we've done is convinced the electrons to move to one side of the object by bringing over a charged object that will either attract or repel those electrons. Okay. So those are your 3 check-in questions. Hope you learned a lot. Let me know what questions you have. Thanks.